So this is week 3, energy system lab 1, and this week I'll have you wire 3 light bulbs in series, take some measurement, then wire them in parallel, and take some measurement. Last week everybody did very well. I'm very proud of you guys. You did very nice. I got all nice, good tight wiring. Everybody light bulb worked. There was no sparks. It was nice. Everybody took their time. I didn't see anybody like trying to rush through it. That's really good. This is how it's done. Take your time, do it correctly, and we get to do measurement. We use the multimeter. We use the voltmeter. I think everybody had their goggles on. Everybody got the proper respect for electricity. I didn't see anybody touching the light bulb by their fingers, touching the wires. So it does happen sometimes. You forget. You don't imagine how fast you forget that there is power going through it. And you see somebody, oh, this is not tight enough, and they go and try to tighten it up while it's already live. So I think everybody did very, very well. So this time we're gonna pick it up a notch, and we'll do 3 light bulbs. It's gonna be the same procedure. We're not going to do the switches because we did that already. I want you to understand how to wire light bulbs in series and in parallel. And you'll be surprised to know that some people still do not see a difference. They will see it in paper, but when they go and try to wire it, they wire things in series. I have my staircase at home is wired in series. That's very not good. So the wires are dim, and if one of them go out, one of them will go out as well. So I don't know why would anybody do that. Probably the person who did the wiring forgot, and or just I don't know what was he thinking. But anyways, they are wired in series. And again, just to repeat, things for safety and control are wired on series, in series. And things that are for loads, give me an example of a load. Motor, fan, light bulb, or condenser, light bulb, heater, whatever thing that consumes electricity, they are wired in what? In parallel. Why?
So if one goes down, the other one goes.
So what?
If one goes down, they all don't go down.
That's one thing, and what else? What happens to the resistance? It drops. What happens to voltage? It stays the same, and that's what you actually after. If one of the components does not get its voltage, it's not going to run properly. Within 10% plus or minus, the equipment is not going to run properly. So you want to have the equipment having the right voltage. So again, we spent the whole week last week, the whole last class, 2 classes, talking about the differences, and again talking about something is different than touching it and feeling it. So we talked about it, we did a few examples. Now we'll do it in the lab, and you'll see the effect, and you'll see it actually happening. So, series circuit, they are wired for safety, which means safety switches, fuses, circuit breakers. Consumes more power if there are loads, but if there are switches, they're not consuming powers, right? Do switches consume power? No, it's a connection. We have one path, and it's very simple. And you do not wire the neutral to each one of them. The series circuit goes through the hot line because we want to cut out the hot line. You'll see in the field sometimes people putting switches on the neutral. That's not a right practice, so be careful with that. This is what it looks like, and probably you can imagine those 3 switches being in series, and it simulates the stuff you have in the board. And this is the hot line, everyone. What color is the hot line? Black, red, purple, blue, green. It's we usually try to use colors to make things easier on us. You will see something like this is a cat cell control. So this will control your gas burner or your oil burner, and all these are all hots. But each one of them energizes a different one, and it should stay on it. And usually in our field, black or red is hot line coming from the wall, and these goes to components. Blue is igniter, pink or purple is oil valve, gas valve, and orange is the motor. But again, they will change. And only one neutral line, which is white. Usually, if you have a bunch of neutral lines that are white, if they are connected together, that's not a problem. You can connect all the neutrals together because again, it's just to complete the circuit. There's no power going to it, just an outlet. So if you mistake the neutral and put them into each other, it's not a problem. However, if you put the hot line to the igniter, to the motor, and you switch them out, that's going to be a problem. So instead of turning the igniter, you turn on the motor. That's why we have colors. So if you go to a job and you find a lot of wires that all are just black with no labels, do the customer a favor and change the wires, or you can at least label them. And sometimes they have stickers where you can label lines. But it's very, very frustrating. Even here in the lab, when somebody doesn't want to take the time and get a different color wire, it becomes frustrating. You'll trace the wire, and suddenly you see a mesh of things, and you get confused, and it's really hard to trace. Okay? So resistances and current, we said the current draw is the same throughout the entire circuit. That's for series. So you're gonna go and measure how you measure the current. What do you use? A clip-on meter. You put the close around the wire and you measure the current at different places. So the current is measured using what? So this is my wire. This is my current. Okay. I'm gonna put on my clip-on meter here, and I'll get a reading. Then I'll put it here, I'll get a reading. This is how you measure current. The multimeter is measuring the electromagnetic field around the wire. You can also put it here, and you'll measure also the current for the entire circuit. So remember, current is measured using the clip-on meter. You can measure small, very, very small current using the prongs, but you have to connect them in series. We're not going to talk about that now. We'll talk about it in the chapter when it comes using multimeter. For now, this is how you're going to measure current. You got to have a clip-on meter with you the whole time to know how much average you're drawing. It looks like magic, right? Because nothing is touchy, but you are measuring actually current. One path for the current to flow. So it's going to be the same here, the same here, the same here. Total resistance is the sum of all resistances. So you're going to add this light bulb and this light bulb. One thing about light bulb, that it's really hard to measure the resistance. Remember the first class when I said resistance changes with what? With two things? One of them was temperature, heat. So when things got hot, the resistance increased or decreased? Increase. So you're gonna measure the light is off, you measure the resistance, and it's going to be, for example, 3,000 ohms. When you turn it on, it's gonna keep increasing. So the power draw will change. That's why when you get a light bulb, I don't know what it's this for, but it's just impressive. So when you look at the light bulb, they don't tell you the resistance, they tell you how many watts. Sometimes it's printed in the top, so when it's dark you can't see it, when you turn it on you can't see it. So if I were to measure the resistance using the ammeter, putting one prong here, I'll get some resistance, right? But that's not the actual resistance. Because this thing gonna heat up like crazy when it turns on.
Does that actually work?
Let's try it out. Now this is great. It's gonna be a blooper. Alright guys, it was not telling you. Yeah.
Oh yeah.
That's really intense and it's hot. What is this for anyway? I have no idea. But anyways, let's look at this nice friendly light bulb. If you look at this light bulb here, It says on it 7.5 watt. Why? Because once it's stabilized and reaches the operating temperature, this is what it's going to consume. So we have watts. What is watt? Watt is power, right? If I want to get resistance from power, what do I do? I can't get resistance from power. I'm going to get the amperage. So I'll get amperage equal power over voltage. What is the voltage of the light bulb?
72.
No. That's the power. What is the voltage?
110.
110, thank you. 110 volts. I divide those by each other. I think it's going to be around 200. Let's go into something very small. So now I have the amperage. What is the resistance? Resistance equals somebody? Voltage divided by amperage, right? 110 again over 0.068. Let's see what that gives. Over. That is very small. So I get here 2,000 ohms. And we're gonna do this math before we before we try the light bulbs. We have 3 light bulbs, yeah.
So before you turn it on, you test it right there to see if that's around it.
Say again?
So before you turn it on, you test it?
Yeah.
If it's around 2000.
But it's not gonna give you 2,000 because it's cold, right?
Yeah.
The 2,000 is when it's completely warmed up. So you can try both. Test it before it's going to be really low, and once it warms up, you'll see how different it is. Just show you the difference. So that's a light bulb. So we have the resistance. We can find the amperage based on that, and we can measure that and just execute Ohm's law and power law. Voltage completely used by all loads. That's so if I go with my multimeter and put the voltage here, it's gonna be 110. If I put it here, it's gonna be 80. If I put it here, probably it's gonna be 0. Everything is completely used. And we'll see that in practice. Yeah, so you're gonna calculate all of them. So you'll have 120 volts here between those 2 lines. However, if you put it between those 2 lines here, it's going to be here and here. It's going to be probably 80. And between here and here, it's going to be 40. Now we'll spend the whole lab in using the multimeter. Did anybody buy their own multimeter? If you did, you can bring it over so you can practice with it. For a parallel circuit, we have more than one path. It's good for redundancy. It lowers the load on the circuit, so you don't have a lot of high voltage draw. So we use that for loads. That's what it looks like. So if I were to connect 3 light bulbs in circuit, pay attention. It's going to be a little challenge. This is my L1. I'm going to go to the first light bulb. And what do? This is L2. Then I'm going to have another fork coming from here to light 2. And I'm going to have another one here to light 3. And each one of those will have its own neutral. So what is the difference here? I did not go from here to here. diverted here. So it forked, and it came here, it split, and it came here. And the neutral does not matter. You can put all the neutral together. If this light has no neutral, what will happen? It will just not light up. But you'll get power, you go with your power, and there's power here, there's voltage, but it's not going to light up because there's no complete circuit. Yeah.
So you can either put a neutral in all three, or you could do three totally separate
Yeah.
neutrals?
Yeah. That's why the neutral is always the same. So it might take you a few seconds to just realize what am I doing here. Just think about how the power does not come out of the equipment, of the load. Each load has its own neutral and its own power. And when I go here, I should measure the current, so the current will split. Do you agree? The current should split. So this current will split into this little one and this one. And this one also will split in two. And this one will split in two. And eventually, all the current coming back here is going to be the same as this one. So this A, it's going to be B, C, and it's going to be D, E, F, G, and here we come back to A.
What do you label it?
Huh?
What do you label it?
The sub currents. Like if this is going to be one value, it's going to turn to two values. And the C here will turn to two values. It's not going to be the same amount, right?
Yeah.
I'm gonna let me just put some bogus numbers so we can make sense. Let's say this is 10 amps. This is going to be 3 amps and 7. Make sense? 3 and 7 is 10. The 7 went over here. It's gonna be 2 and 5. 2 amps, 5 amps. The 5 went out in here, and the 5 became 2 and 3. And eventually, this will add up here. They all pull into the same current. This is going to come out of here as 3. This is going to come out of here as 2. This is going to come out here at 2, 2, 2, 2. And I'm going to have 5 coming back in here. So it's going to be back at 10 amps. I don't want to confuse you. Well, then, yes. He asked for it. It's if you're gonna be an electrical engineer, you use something called pressure flow, which basically every subcircuit will have the same amount of amps. We don't want to go this deep. Just understand that the current will split and go back to the same. This is the extent of what we need to know. Try to focus on things that you're gonna need, and weed out all the stuff that not necessarily you know. Unless you're really interested, unless it's going to be your field, something you're going to do on a day-to-day basis, focus on that. They always say it's better to focus on your own strength and build on it. Resistance, they get smaller, and this is the addition we did. So we'll do the same thing to know what is the total resistance for the circuit. We add it together. And voltage, that's the main reason we do parallel circuit, is the voltage is always going to be the same. You agree? You're confused. You're a hands-on kind of person, aren't you?
Uh-huh.
You're a hands-on kind of person.
Yeah,
Yeah.
very much so.
Okay.
And the visual there.
Yeah, take a visual picture of it, then we'll go and execute that in the lab. I'm kind of like that. If I don't see it, I can't really. I can't really like comprehend. Show me. That's why a lot of mechanics are like that. You can describe their problem in the phone for 10 hours. So just bring it over. Just bring it over. And you open the phone and look at it. Oh, okay, here it is. And some people just listen to it and go. People learn and observe things differently. This is just a good analogy between a water circuit and an electrical circuit. And if we think as a resistance, as a pinch in the line, this is the resistance, and the flow being the current, and the pump is providing the voltage. So this is some analogy I got that I found very interesting. If you can just comprehend what's going on. The voltage is basically a pump pumping the flow, and the flow is the current, and the resistance is a small pinch in the line. If it makes any sense to you at all. You like it? That's okay. This is our friendly board. We did that part already, all the way here. Everybody succeeded. was excellent. Now we're gonna add 2 more light bulbs. You can do 4 if you want to, but no need. If you get 3, you will get the idea. And this time, when we're gonna come out here the same way. 1 neutral and 1 hot. However, you're gonna get the neutral to go into 3 ways and the hot to go 3 ways. Any way you want it. Make sure you have very solid connection, same as before. And those screws in the light bulbs are very annoying, so try to find a way around it. I tried to find those in the shop, with new ones, but I couldn't find any. They're very old, but they're very convenient because you have the wires from the outside and the inside. And we'll go and measure the resistance in each one of them. We'll clip it on each one of them and measure the resistance. Measure the amperage. And the resistance we can do mathematically. Then we'll go with the ohm meter and measure it, and it's supposed to be much smaller than it is. And I'll show you this. And if you are curious, you can turn the light on until it's hot, then turn it off, and right away you put the meter, and you can see it drop as it cools off. Keep dropping, which is very interesting. Okay, that's why also if you look at motors, have you seen really any motor above 1.5 horsepower, like big pump motor? What do they usually have on them? In the back. It's always a fan to cool it off, because if it heats up, it's not going to produce, it's not going to work the same way. So cooling is very, very important. Does your car perform very well if it overheats? No. Does it perform very well if it's cold? No. So it has a design temperature. When you turn on the car, it has to heat up a little bit until the motor becomes smooth and it functions properly. Then they keep the temperature using a thermostatic valve at some certain temperature. If you're going through the mountains with a car that's not designed for a lot of incline, you'll see the car becoming very sluggish because it's not keeping up with the temperature. Temperature affects the material in many ways. One of them is resistance and conductivity, and the second way is also expansion. Things do expand when they're hot, so you got to think about that. So there is a design temperature where the material will expand in a way that it might break the system. Like if your engine overheats and you don't stop, what will happen? You break your engine block. It will expand and it's beyond the limit, and it will break the engine block. It might melt. It might weld itself to each other because it's a lot of temperature. So for this semester, that's what I want you to know. That's going to be the electrical part, which is 3 light bulbs. Then we'll move into some mechanical parts. All in preparation for you to know all the components for oil and heating. So after that, we'll go into pipe, soldering, and other things. But if you know how to do basic wiring, next semester we'll continue into the thermostats and aquastat and other components. Use of the meter. So this is the shortcut for the resistance for these 2 equations. If I find it easier to do the 2 equations, if you want to get the shortcut, this is how it's done. We can predict the resistance based on the watts of a light bulb. We can measure the amp drawn by circuit in series and parallel, and we can measure the total resistance of both circuits. This is something I've seen a lot of people in the field doing. See the 4 things that we need: power, volts, ohms, and amps, and all the other combinations. If you really have the 2 triangles, you don't need this.
Can you go back one?
Yeah. Got it. So if you want, you can print this and use it. But rather, you have something really simple you can use, which is Ohm's law and power law, and derive whatever you need out of that. So you're always looking for like 4 components. And this circuit looks very intimidating to me. Too many objects, but whatever works for you.
It's the same thing, right? Like
Yeah.
just-
Yeah. So this is basically saying if you want the amperage, you can do these three things together. If you want the resistance, you can get any of those 3 things together. So I'd rather if you just do whatever is comfortable for you, and you can print out this circuit over here. I think I have a small card that I can give you too, if you want. I have extras. go to any hardware store, probably they sell those.
Yeah, no, but his house is not
You can bring it to the examiner, you can understand what it means. And it's really hard. It's actually older than me. Came from the last century. Yeah, yeah. It's given the U.S. Army.
What is this, Rickman?
He said,
Okay. Until then, for this lab, we'll do this week. What I need for you to have is goggles, please, all the time. Please just proceed the way you are. You guys are doing really great. I want the same attitude, the same patience, and just keep with the same pace. And so far, so good. Okay? Any questions? Simple. Thank you.